Now for problem 6, it says a pendulum of length L has a period of 2 seconds on the Earth. If the same pendulum is brought to another planet where the period is 4 seconds, what would be the gravitational acceleration? There's a few ways you could do this problem. You can sort of do it. You could have done it similar to how problem 1 was done by beginning with writing the formula for the period of a pendulum. And I'm going to use, since they're using for L, I usually use the small l, but they are calling it capital L. So let me be consistent with what they're using for variables. So there's my formula for the period of a pendulum. So I could figure out, just change this to from 2 to, but basically what's happening is the period is being doubled. So if the period is being doubled, I can figure out what needs to be done here so that that's doubled. Now, if that's doubled, I've got 2 choices. I can either make that 4 times what it was, which would double that, or I can make that 1/4 of what it was, and that will double that. And that is, if I make whatever 1/4, that's going to be the answer. But let me show you another way of doing this, where since I'm using the same pendulum, I know what gravity is on the Earth, I know what the period is on the Earth, so let me solve for L. And then once I have L, then I can just rearrange this equation to solve for G with the new period. So if I take this, and a lot of people tried this, but they didn't do the math right. So if I square everything, so I'm going to take this whole equation, and I'm going to square it. So when you square t, you get t squared. When you square 2, you get 4. When you square pi, you get pi squared. This is the part that people didn't do. They got rid of that in the square root, but they left that as 2 and pi. So 4 pi squared L over G. So I want this one solved for L, and then I'll know what the L is for the pendulum that is brought to the other planet. So if I rearrange this thing to solve for L, I'm going to bring that up there and the 4 pi squared down there. So it's going to be L is going to equal GT squared over 4 pi squared. So we know that on Earth, gravity is 9.8 meters per second squared, and you could use, some people use 10. On Earth, that period is 2 seconds, so that's 2 seconds squared, divided by 4 pi squared. And let's see. Okay, I didn't do it that way. I did it the way of just knowing that it would be 1/4. So what does that work out to be? Does anybody have the answer for that? I'm getting 0.99. 0.99. I'll put in 0.99. We'll see if I get the answer. So 0.99 meters. And so now that I know the L, I'm going to now take this equation and solve it for G on the new planet, because we want to figure out what the gravity is on this other planet. So since I already have this G representing G for the Earth, what I'm going to do is I'm just going to move the G up there and the T squared down there. And I'm going to say that G on this new planet is going to be 4 pi squared L over T squared. So it's going to be 4 pi squared L, I'm going to put in 0.99 meters, divided by the T on this other planet is 4 seconds. So it's double what it was on Earth. And actually, I'm looking at that, and if I solve that, I should get 1/4 of that. Well, I should get. Let me see. I'll just work it out. So 4 times pi squared times 0.99 divided by 4 squared. and I get 2.44. I know when I did the other way, again, because these numbers might have been rounded off a little bit, but I think I got 2.45 when so that's going to be 2.45 meters per second squared. That's your answer. So I know when I did it the other time, I just had 9.8, and I knew that on the other planet it had to be 1/4 of that. So if you take 1/4 of 9.8, it was 2.45. So it's a little bit different doing it this way than if I had just said, well, it's going to be 1/4. Any questions with that?